My name is Joshua Mangelson. I'm an assistant professor at Brigham Young University, where I run the Field Robotics Systems Lab at BYU. And in my lab, we're particularly interested in developing and solving perception, localization, and mapping problems that enable us to be able to place robotic systems in real-world, unstructured environments, like Margarita said, and where they can perform real work. And we're interested in doing that particularly in the marine domain, though we also do it in aerial and in ground in a couple different contexts. I've been at BYU for about 5 years. My tenure packet goes in this summer. So I've been thinking about kind of the creation of the lab and the decisions I made in doing that. I've been really thrilled and happy with that. But I've had a bunch of colleagues and friends who maybe did marine robotics or field robotics in the past, and then when they started a faculty position decided not to because of the risk and the challenges. So I kind of wanted to talk through some of the challenges specific to marine robotics, but field robotics more generally, and then talk about why it might be useful to do marine robotics or field robotics anyway, in terms of those challenges. So to jump into that, Louis Wickham used to say that placing an electronics system of any kind in salt water is a highly unnatural thing to do, and that's absolutely the case. We're kind of fighting challenges in every direction when we do this, right? So one thing to think about here is that water absorbs electromagnetic signals. So once you get about an inch underwater, you lose GPS connection. And you also lose Wi-Fi or radio connection to your vehicle, which is the typical technique we typically use to operate and control our robotic systems. So the way that we deal with this is we use acoustics. Acoustics are really useful because they're able to transfer much further in the water, but they're much, much slower. So typically we're able to get communication to these vehicles on the level of 8 to 10 bytes per second, and only one vehicle can kind of talk at a time, and if there's any kind of problem, you won't get those packets at all. So that's a major problem. We have similar types of things that happen with light. So once you dive in most bodies of water, you immediately lose visibility, which is something that is hard because we typically use cameras on a fairly consistent basis in robotic systems. We again turn to acoustics to be able to handle this. So we send out sound through the water, it bounces off of objects and returns, and then depending on the type of sonar modality we have, we can then process that data in order to observe the scene using sound. But this brings its own challenges because sound is noisy, and there's a variety of different types of sensors and sonar sensors that you have to deal with that are fundamentally different from how cameras work. If you are able to observe the scene, typically the scene itself is fairly useful in terms of localization. So typically there's a lot of ripply sand that's repetitive with fairly few features that you could use to try and track your position. And then the scenes themselves are typically fairly dynamic. So this happens on multiple time scales. So we've got waves on short time scales, which will move your vehicle and change the scene. Then you've got tide on the order of hours, which will, in some areas of the world, change things on the order of 10 to 20 feet over the course of a mission. And then you've got storms that will dramatically change the scene at unknown times, right? And then in addition to that, you're typically operating in an unknown, complex environment. So this video is of a robotic system that was, its echo sounder is detecting a rocky outcropping that wasn't in the previous map. And then as the robot scales, it's trying to avoid that rock. It's not able to quite do that, and we end up hitting the rock here. Luckily, our safety code kicked in, and we were able to have this robot return to us. But typically in the marine domain, if you have something go wrong, you might lose the entire vehicle. And it's pretty common for most marine roboticists to have lost a vehicle at some point in their past. I know Matt has. So one thing to think about here is also these systems are fairly expensive. So if you lose one of these things, or if you're trying to operate in these spaces, you're going to have to come up with a significant amount of funding in order to repair the vehicle, maintain the vehicle, or to just deploy them at all. So there's a wide variety of challenges, and I think I'm talking specifically about the marine space here, but I think that these similar types of challenges appear all throughout field robotics in general. So if you think about why would we even do this, right? If it's this challenging, why would we do this in academia? I think, first of all, it's just an awesome place to be, right? I get to spend a lot of my time out on coastlines. This is a picture from right outside my hotel, right by BYU, Hawaii. On the bottom left, there's a pod of dolphins that tapped and swam by right as we we're operating and doing testing. And then there's a lot of unique history and culture as well. So this is a picture of me and some of my students on Hokulea, which was the first native Hawaiian canoe in recent years to circumnavigate the world with no GPS and no electronic navigation. So there's some really, really cool things you can do within that space. But then setting that aside, I think there's potential for us to make a real difference in the world by trying to tie our research directly to problems that actually are facing society in general. So to touch on some of those real quickly here, I believe we have a responsibility to be stewards of planet Earth. And 70% of the Earth is covered by water. And according to NOAA, more than 80% of that is unmapped, unobserved, and unexplored to a significant degree. We also have problems with civil infrastructure. So the American Society of Civil Engineers provides a grade to the United States infrastructure on a yearly basis, and we typically get a failing grade. So one thing to think about this is that a large majority of this infrastructure is underwater, and the way it's in need of typical and regular inspection at much larger rates than it currently is being done. And then our modern world is really based around marine operations, whether we realize that or not, right? 80% of our goods are transported over water, and 60% of food is transported over water. And then, of course, there's a variety of defense reasons why marine operations are important. So in my lab, we're looking at all of these different directions in some form, and I wanted to take the rest of the time to kind of touch on each of the projects that we're doing within this space. So the island of Molokai, Hawaii, is home to the largest fringing reef in the United States, and it's currently being destroyed due to sedimentation and erosion from the mountains on the southern shore of Molokai. And manually sampling this space is really challenging to do. It's costly and difficult to do at scale. So we're working with BYU Hawaii, local coral restoration nonprofit groups, to map the southern shore of Molokai and try and characterize the health of the reef at these sites, as well as other sites on Oahu as well. And we're doing this both with surface vessels and underwater vehicles. This is just some pictures of some maps that we've developed that we then pass off to our marine biologist colleagues to do processing and kind of analyze what's going on in the scene. And this has been a really wonderful project to be involved in, and we're excited to continue working on this. On the infrastructure side, my PhD work was focused on autonomous ship hull inspection, and so we were building robotic systems that would navigate underneath a ship, use camera and sonar to navigate and map that and inspect the ship for problems. We were using SLAM techniques in order to try and ensure that we got full coverage of the ship by performing loop closure in real time, and then trying to determine how much of the ship had been covered with our sensor platform. And this is something that while we're not doing at BYU right now, it's something that we're still heavily interested in. Michael Kess and I have started a startup called Aquatonomy that's looking to extend some of this previous work and branch into infrastructure inspection. And we're hiring, so if there's marine robotics who are interested, marine roboticists who are interested, please reach out to me. We're also thinking about underwater localization in a variety of different contexts. So it's pretty common that you have teams of agents of different types that need to work together in order to reliably conduct some types of tasks. So if you're searching for something on the seabed, for example, you might have a torpedo-like vehicle that has something called side scan sonar, and it maps the seafloor, but is only able to navigate at high speeds. And then you might want to deploy a robotic system that has a hovering potential or maneuverability, but those sensors, those vehicles typically have what's called a forward-looking sonar, as opposed to an imaging sonar or a side scan sonar. And so we're thinking about how do we do localization across these modalities. If we have a map of the seafloor in one context, and then we want to localize using a different type of sensor, how do we do that? And then we're thinking about the epipolar-like constraints that enable us to map features between these modalities. And then we're thinking about how do we do feature-based matching between those modalities as well. So then we can start to do localization across these modalities. We're also thinking about other methods for doing localization. So one of the ways you can localize is to use bathymetry. So if you have a previous map of the seafloor, you can then have your robotic system ping the seafloor on some regular basis, and if you compare what the robot's seeing in real time to the previous map, you can improve your estimate of your localization. But that depends on your robotic system actually passing over an area of the bathymetry that is actually varying. So we're then thinking about if we have teams of agents that are all cooperatively doing this together, you can then maintain a relative pose between the agents and then improve your estimation by using shared information. But you then have to do this over acoustics with that really, really small throughput and potentially really lossy communication that I mentioned before. So this is something we're working on heavily. We're testing this both with industrial IVR underwater vehicles, as well as building a fleet of low-cost vehicles so that we can scale this to many, many vehicles as opposed to just 2 or 3. To support these projects, we've been developing a simulator called Hollow Ocean, which enables us to be able to simulate all of the different types of sonars we need, acoustic comms. It's all based on Unreal, which enables you to be able to very quickly build environments and incorporate information that's already built into the Unreal system. And then it's all wrapped in a simple Python interface, which makes it really easy to use. And so we've had a lot of people interested in this, and it's open source. So if you have questions with that, let me know. Our hope is that we can get more people involved in the marine space through this, even though the costs are significantly high in terms of actual operation. And then we're also thinking about surface vessel autonomy. So if you have a surface vessel that's operating in close proximity to like a river or a harbor of some kind, you need to be able to think about how we can interpret and map and understand the scene within that space. So we're thinking about localization using a variety of different types of inputs, and then we're thinking about mapping. So we're building a sensor platform that has IMU, high fidelity cameras, dense LiDAR, and we're thinking about building maps and data sets that enable us to start thinking about how do we perform SLAM and mapping in a high fidelity way in these domains. And that's something we're hoping to release in the next little while. And then we're also thinking about how do we understand these scenes? How do we interpret these scenes? So once we're able to build a map, are there ways, how do we interpret the scene in such a way where we can perform many tasks by using semantics? And so we're building LiDAR point clouds that we're able to query so that we can try and specify, I want to build a map once and then be able to perform many tasks within that scene. And that's something that we're working on both in the ground context, but the long-term goal is to do that in coastal zones. Okay, so kind of in summary here, I found marine robotics to be really rewarding, and field robotics enables you to kind of ground your research in problems that are directly relevant to society, and then be able to see those things actually work, right? And that's something that I've been really thankful for and enjoyed over the last 15 years, 10 years. I also just want to say thanks to my students, because they're the ones who are doing the majority of the work here, and thanks to our sponsors, and I'm happy to take any questions. Thank you.
Any questions from the audience? And there are mics out there. Great, I have a question. You want to tee up, Tobias? You know, Josh, one of the things that I think about a lot is, you kind of highlighted this, it's hard to get people to go into marine robotics, and when you're in marine robotics, it's hard to do it pre-tenure, and it's all these risks and all that. Are there things we can be doing as a community, not just for marine, but for just generally thinking about field robotics broadly? Like, how do we make it easier for people coming up behind us to do this kind of work and not get punished?
So I think that I think open source platforms, open source simulator tools, but also just the platforms themselves is something that can be really useful and helpful within that space. Marine robotics is growing, right? It's still a very tight-knit community, really small, but there's more and more people getting involved. And I think a big part of that is because there's been small startup companies who have developed the ability to provide low-cost components, right? And that has enabled more and more people to get involved in the scene. So I think releasing designs, releasing the ability to be able to build these robotic systems and kind of maybe coalescing around some tools that are useful is one way that could happen. But I think it's a really useful, I think it's an exciting area to be in. It's very unique and fun. And I think that there's really cool things from that perspective. There's big potential to make a difference. But I'm hoping we can get more people involved.
Me too. And the work you're doing in open sourcing that Hollow Ocean, plug for Hollow Ocean, I think is super important. So thank you for that. And join me again in thanking Josh.